How real-time data predicts bottlenecks before they happen. Most organizations identify a bottleneck after the damage is already visible. Production is delayed. Work begins to accumulate. A machine stops. Orders miss their deadlines. Employees start working overtime. Managers begin changing priorities. At that point, the bottleneck is no longer a warning. It has already become an operational failure. But modern processes generate signals before the failure happens. Cycle time begins to increase. Queues start growing. Equipment performance slowly deteriorates. Process variation becomes wider. Maintenance alerts appear more frequently. The system is communicating. The problem is that many organizations do not recognize the message early enough. In this video, we will examine how real-time data, leading indicators, statistical process control, dashboards, and automated alerts can help organizations predict bottlenecks before they stop production. This is the final episode of Modern Lean Six Sigma: Hidden Failures in Operational Excellence. A bottleneck is any point in a process where demand begins to exceed the capacity to complete the work. It may be a machine, a department, an approval step, a specialist, a loading dock, a software system, or even a decision that only one manager can make. Bottlenecks rarely appear instantly. They usually develop through a series of small signals. A machine takes slightly longer to complete each cycle. A queue that normally contains 10 orders begins holding 15. A maintenance team receives more minor alarms. A specialist has more unfinished requests. A production step begins using overtime more frequently. Each signal may appear manageable, but together, they indicate that the process is losing its ability to absorb demand and variation. The earlier the organization recognizes this condition, the easier it is to respond. The objective is not to predict the future with perfect certainty. The objective is to identify increasing risk before the final failure occurs. Many organizations believe they have real-time management because they use dashboards. But a dashboard alone does not create prediction. It may simply display the failure faster. A screen can show that production is late. It can show that inventory is increasing. It can show that equipment has stopped. But these are often lagging indicators. They confirm what has already happened. Predictive operational management requires more than visibility. It requires understanding which process signals appear before the final result. A useful real-time system should help answer questions such as: is cycle time beginning to drift? Is the queue growing faster than normal? Is equipment performance becoming unstable? Is demand approaching available capacity? Are repeated minor stops becoming more frequent? Is work in progress accumulating before one process step? Is the process still stable, even if it remains inside specifications? The dashboard should not only describe the current state. It should reveal the direction in which the process is moving. A leading indicator changes before the final operational result. It provides an early warning. For example, late deliveries are a lagging indicator. They confirm that the customer has already been affected. A growing production queue is a leading indicator. It suggests that the process may not have enough capacity to protect future delivery. Equipment failure is a lagging indicator. Increasing vibration, temperature, or minor stoppages may be leading indicators. Customer complaints are lagging indicators. Increasing rework, response time, or repeated process exceptions may be leading indicators. The strongest predictive systems connect leading and lagging indicators. They show how early process behavior is connected to future business performance. This allows teams to act before the customer sees the failure. A company should not wait for late orders if the queue is already growing every hour. It should not wait for a machine to stop if performance data already shows abnormal deterioration. It should not wait for quality complaints if process variation is steadily increasing. The value of real-time data is not only knowing what is happening now, it is recognizing what is likely to happen next. One of the earliest signs of a bottleneck is increasing cycle time. A process step that normally takes 5 minutes begins taking 5.5, then 6, then 7. The change may appear small, but if demand remains constant, work begins to arrive faster than it can be completed. The queue starts growing. This is an important relationship. When cycle time increases, capacity decreases. When demand exceeds available capacity, work in progress accumulates. As work in progress increases, lead time becomes longer. The process may continue operating, but the system becomes less responsive. A real-time dashboard can track average cycle time, median cycle time, maximum cycle time, queue size, arrival rate, completion rate, work in progress. The most important insight is often not the current number. It is the trend. A queue of 20 orders may be normal in one process and dangerous in another. The organization needs a baseline. What is the expected range? How quickly is the queue growing? Is the completion rate falling below the arrival rate? If new work enters faster than the process can complete it, the bottleneck is already developing. Statistical process control is especially valuable because it helps organizations distinguish normal variation from meaningful process change. Every process varies. Cycle time is not identical every minute. Machine performance changes slightly. Demand moves up and down. Not every movement requires intervention, but some patterns indicate that the process is changed. A control chart can reveal a sustained shift above the center line, a gradual upward or downward trend, repeated points near a control limit, a sudden point outside the expected range, unusual cycles or patterns. These signals may appear before the process violates a specification or misses a production target. This distinction is critical. Specification limits describe what the customer or business requires. Control limits describe how the process normally behaves. A process can remain inside specification and still show evidence of deterioration. For example, cycle time may still meet the required target, but a clear upward trend suggests that the process may soon become incapable. SPC allows teams to investigate the change while there is still time to act. The goal is not to create more charts. The goal is to detect meaningful signals earlier. In manufacturing, equipment often generates useful warning signals before a major stop. Temperature changes. Vibration increases. Energy consumption rises. Minor stoppages become more frequent. Cycle time becomes inconsistent. Tool changes happen earlier than expected. Defect rates increase under specific operating conditions. Individually, each signal may not justify stopping production, but together, they may indicate declining equipment capability. Real-time monitoring can connect these variables. For example, the system may identify that increasing vibration is associated with longer cycle time and more defects. The machine has not stopped yet, but its effective capacity is already decreasing. This is important because a bottleneck does not require complete equipment failure. A machine can become a bottleneck simply by operating more slowly or less consistently. Predictive maintenance and Lean Six Sigma should work together. Maintenance data helps identify equipment deterioration. Process data shows the operational impact. Quality data reveals whether performance loss is increasing defects. Together, they provide a more complete view of risk. A good operational dashboard is designed around decisions. It should not display every available metric. Too much information creates noise. Managers may see dozens of charts without knowing what requires attention. A useful bottleneck dashboard should focus on a limited number of signals. Current throughput, demand versus capacity, queue growth, cycle time trend, work in progress, downtime frequency, quality losses, constraint status. It should also show context. Is the current value normal? Is the trend improving or deteriorating? What threshold requires action? Who is responsible for responding? A dashboard without response rules becomes digital decoration. People look at it. They discuss the numbers. But the process continues unchanged. A strong dashboard connects information to action. When a threshold is crossed, the team knows what to investigate. When a trend appears, someone has responsibility. When the bottleneck moves, the system helps the organization adjust priorities. Visibility is only useful when it changes behavior. Automated alerts can support early intervention, but poorly designed alerts create another problem: alarm fatigue. If employees receive too many notifications, they stop treating them as important. Every small movement generates an email. Every minor delay creates a warning. Dashboards remain red for long periods. Eventually, alerts become background noise. Effective alerts should identify meaningful conditions. A single unusual data point may require observation. A sustained trend may require investigation. A growing queue combined with declining completion rate may require immediate capacity action. The severity of the alert should match the operational risk. Alerts should also communicate clearly. What changed? Where did it happen? How serious is it? What action is expected? Who owns the response? An alert that only says performance problem provides little value. The system should help the employee understand what condition requires attention. Technology should reduce response time. It should not create more confusion. Real-time data is only useful when it is reliable. A fast measurement can still be wrong. Sensors may be poorly calibrated. Employees may use different definitions. Systems may record timestamps inconsistently. Manual entries may be incomplete. Equipment may remain connected while producing misleading values. Before using data to predict bottlenecks, organizations should confirm: is the measurement accurate? Is the definition consistent? Is the data complete? Is the collection frequency appropriate? Does the measurement represent the real process? Measurement system analysis remains important even in digital environments. Automation does not eliminate measurement error. It can automate measurement error at a much larger scale. The organization should also avoid confusing correlation with cause. A dashboard may show that two variables move together. That does not automatically prove that one variable causes the other. Operational knowledge, Gemba observation, and root cause analysis are still necessary. Data provides the signal. People must interpret what the signal means. Technology can show where performance is changing, but it does not always explain why. A queue may be growing because of equipment deterioration, or because information is incomplete, or because a new product requires more processing time, or because employees are correcting defects from an earlier stage, or because priorities change too frequently. The dashboard reveals the symptom. The Gemba reveals the operating condition. When real-time data identifies an abnormal trend, teams should go to the process. Observe the work. Speak with employees. Check materials, machines, methods, measurement, environment, and workload. Compare the data with reality. This combination is powerful. Real-time data provides speed. Gemba observation provides context. Lean Six Sigma analysis provides discipline. Together, they allow organizations to move from signal to cause and from cause to preventive action. Predicting a bottleneck has no value if the organization does not respond. A preventive system should define action before the crisis occurs. First, identify the critical process steps. Which resources could stop or severely limit the entire value stream? Second, select the leading indicators. What signals appear before capacity, quality, or flow deteriorates? Third, define normal operating ranges. What level of variation is expected? Fourth, establish warning and action thresholds. When should the team observe? When should it investigate? When should it intervene? Fifth, assign ownership. Who receives the alert? Who has authority to act? Sixth, define possible responses. Adjust the schedule. Reduce work release. Move resources. Perform maintenance. Correct material or information problems. Protect the bottleneck from unnecessary interruptions. Finally, review the result. Did the action prevent the bottleneck? Was the warning early enough? Should the threshold be changed? Prediction improves through repeated learning. Reactive organizations spend their energy recovering from problems. They expedite orders, change priorities, call emergency meetings, use overtime, move people between departments, negotiate delays with customers. Preventive organizations use early signals to avoid those conditions. They do not eliminate every disruption. No process can predict every event, but they reduce the number of surprises. They recognize deterioration earlier. They create response plans. They protect critical capacity. They use data to support decisions before urgency takes control. This is one of the greatest contributions of modern technology to Lean Six Sigma. Digital tools allow faster measurement. Sensors allow continuous monitoring. Dashboards provide visibility. Analytics reveal patterns. Automated alerts reduce detection time. But the purpose remains deeply connected to lean thinking. Make abnormal conditions visible. Respond quickly. Protect flow. Prevent waste. And improve the system. Bottlenecks do not always begin with a complete stop. They begin with signals. A cycle time that slowly increases. A queue that grows every hour. A machine that becomes less stable. A process with increasing variation. A resource approaching its real capacity. A growing number of exceptions. Real-time data helps organizations see these signals earlier. But prediction requires more than collecting information. The data must be reliable. The indicators must be meaningful. The dashboard must support decisions. The alerts must lead to action. And teams must connect digital signals to the real conditions at the Gemba. Modern Lean Six Sigma is not about replacing people with dashboards. It is about giving people better information before the failure becomes unavoidable. Do not wait for production to stop. Do not wait for the customer to complain. Do not wait for the monthly report to confirm the loss. Measure the process. Watch the trends. Understand the variation. Define the response. And see the bottleneck first. Because the best operational problem is not the one your team solves quickly. It is the one your organization recognizes early enough to prevent. This concludes the first series of Modern Lean Six Sigma, Hidden Failures in Operational Excellence. Across these 8 episodes, we examined automation, small deviations, process documentation, operational debt, feedback loops, resource utilization, psychological safety, and real-time bottleneck prediction. Each topic reveals the same principle. Operational excellence is not destroyed only by major failures. It is often weakened by hidden conditions that organizations accept, ignore, or recognize too late. Subscribe to the Lean Six Sigma channel and continue exploring practical strategies for building stronger, simpler, and more reliable processes.